Okay, guys, let's look at this question here. We have to figure out which one is representing conjugated multiple bonds out of those four structure. Which one? Somebody will tell me. So this one here, you can tell that's not part of it. Conjugated double bond is double bond, single bond, correct? Double bond, single bond, double bond, single bond, and etc. Correct? So this is here, double bond here. However, we have two single bonds after that. That's not the case. How about here? This is not the case either, because you have a double bond here, single bond. Here should be double bond, but it's not. So that's not the case. How about here? Double bond, single bond, double bond. This is correct. This structure really representing a conjugated system. How about here? Double bond, single bond, double bond. That's correct too. So we have two structures. They really, both of them have a conjugated multiple bond system. The other ones are not. You have to have a double bond followed by single, and the single followed by the double. So alternating. We call this conjugated means, as I said, alternating. And we mentioned that before, that this conjugated system is causing the system to be very, very stable, because the double bonds migrate. So the double bond can migrate from one side to the other side, and it's delocalized. So alternating leads to, we call it delocalized double bond system, double bond system. So more stable, stability is very, very high. That can be seen in a higher boiling point, in higher melting points. All the physical properties will be very, values very, very high. Okay, guys, so let's go for the next topic. Nomenclature, we talked about this before, because this is in alkanes as well in alkenes and alkynes, all the hydrocarbon. As a matter of fact, all the organic chemistry, always our base is the longest straight chain. That is the whole goal, to have to pinpoint where is the longest chain, but straight chain. We are not looking for a branch chain. That's not the case. That's not the case. Always the skeleton, this makes the skeleton of the organic structure. That is the skeleton of the organic structure, correct? So that's not the case. So this is not the case. We have to see always longest straight chain, correct? So that's the case. It is so. Here, just the same thing in numbering. Here you can see we are looking at the longest chain, and now we have a double bond and triple bond. If we have a double bond, remember, skeleton is longest straight chain, correct? That's the skeleton. Besides this, when we have a double bond, always the double bond, double and triple bonds, will be given the lowest numbering, will be given the lowest numbering. You cannot give, always remember, not only the double bond and the triple bond, even when it comes to attaching those branch group or substituents, always we look at the alphabets, correct? As we've seen, A will come before B, B will come before C, and so on. And then you have to look at where you find the lowest numbering of those groups. So don't take always the largest numbering. It has to be even for those substituents. You look for the lowest numbering. Now here, this number here, carbon is 2. The double bond start with carbon 2. Now if we are going from left to right. However, if we go from right to left, this will be number 3. Which will win? Will win number 2. We have to have the lowest numbering for double and triple bonds. Correct? Always remember that's the case. So the skeleton is made of the longest straight chain. Correct? The double bond, triple bond, when they are present, they have to have the lowest numbering. This is not true. This is number 3 here. 3. Number 3. This is number 2. The lowest numbering 2 is lower than 3. Okay, guys. So 2 is lower than 3, and that's the name of the structure will come out. Now, if you look at the second example, let me change the color here. Now we have to go from, again, always from left to right or right to left. Always make yourself those arrows, and then see which direction will lead to the lowest numbering. That will be your correct structure. Correct. So if I go from left to right, the double bond is number 2. Correct. Everybody's following? If I go from right to the left, so here's number 2, and here is this one is identical, by the way. So if you look at this from 1 to, this is number 2 too, so that's identical. But what is meant if I have something like this? Correct? If I go like this, this will be number 3. This is not allowed. This is the same, identical. If I go from right to left, the double bond is still number 2. Correct? Here is number 2. But if I have something like this, from right to left, and the double bond now is number 3, that's not allowed. That's higher numbering. Correct? So let's go further. And the only thing is to know this is exercising. You have to look at Chem 101 homework and look at the exercises there. So let me take this one out and go further here. And this one here will tell you the same thing we did, just some examples here. All the time, try to go to left to right, and then try to get from right to left, this arrow. Which one will lead the lowest numbering? That's the correct structure, and you name it as such. So this one going, the double bond is 2. If I go the other way, the double bond is 3. The 2 will win. Correct? This one is number 1, by the way, sorry. This is number 1. Correct? Not here. This is number 1, the double bond. Correct? And if I go where? If I go from if I go from left to right, it will give me carbon number 1. If I go from right to left, this will be number 1. Now I'm looking at this. 1, 2, 3 will be number 3. Number 3 is higher than number 1. So the option from 3 here, double bond number 3, the double bond here, number 3, and here is the double bond number 1. So the 1 will win, and it is here 1 butane. Correct? Now the naming of this, You are numbering of the carbons. The carbons are 4. That's bute. Correct? The double bond is coming at the first, the lowest numbering. 1 bute. Since it's a double bond, then I will add to this E-N-E. Correct? So we have 1 designate the location of the double bond. This one here designate number of carbons. Correct? And here is designate type of the bonding. Type of bonding. So we have a double bond here, not a single bond. If it's single bond, will be A-N-E. If a triple bond, will be Y-N-E. Yeah. Yan, alkyne, ine. Okay, guys? And this is the same thing. You can look into this example here. Now you have two, again, go from left to right or from right to left. Which one will lead to the lowest numbering? That will be your structure. So we have here 1 and we have here 3, which is this one here. If I go the other side, will be 3 and 4, will be 3 and 4, correct? So if I go from here, this is 1 and 3, and this one will be 1, 2, 3, correct? 3 and 4. So this one is 3 and 4, which will give us a lower number is this. So from left to right, give us the lowest number. 1, 3 is this, those two double bonds, 3 and 4. So since we have a double bond, so 1, 2, 3, 4, 5, that's, first of all, we have to designate where are those double bonds. We said 1 and 3, so 1, 3, correct? Then I will say I have how many? 5, that's bent, correct? And then I have double bond, E-N-E. However, I have now 2 double bonds. I will add what? Di. So di will give you how many? How many? Now we have introduced how many? This one here means type of double, this is double bond, type of the bond, double bond. Bent is number of the carbons, carbon number. And here designating the location of where are those 2 double bonds. They're hooked up to 1 and 3, not the 3 and 4, that's large number. It's not considered. So, let me go further.
Wait.
Yes. Yeah.
The second one, it wouldn't be on the,
Those you have 5. You have 5.
that's 1 and 3, it wouldn't be 2 and 5? Or
2 and 5? No.
It wouldn't be 2 and 4?
No, that's you always the number of the double bond. Where it starts?
Where it stops?
The starting of the double bond, not the end of the double bond. Always the numbering is the start of the double bond or triple bond. Start of double bond, or triple bond. Always the start, not 2. No, not 2. That's the end of the double bond. Start with 1, not 2. Always the start, correct? And the second one starts on the third one, not on the fourth, correct? So let's go further, and this is the same thing. Now we have to look at the priorities. Now we have the double bond. We know how to do to number those double bonds. If there are more than 1, then you have 2 of them di. If there are 3 of them, tri. And if there are 4, will be tetra. So whatever. If there are 5, penta. So pentadiene. So here it is, pentadiene. So now, if we have, what will happen if we have 2 double and triple bonds? it turns out your priority will come that you give the first priority for the double bond. So the double bond will take the first priority, then the triple bond. So you name this one here as priority will be taken by the double bond. Okay, with the numbering, with what? With the numbering. So you have 1, 2, 3, 4. If you go again, always left to right, or the bottom right to left. So the numbering here is always the double bond will take over. You don't start with here number 1, like here. See, you don't start this number 1. That's not allowed. Why? The rule is the double bond takes first priority over the triple bond when it comes to numbering. Correct? So, meaning when I say this, this will have the priority means the name will be taken as alkenes, E-N-E. So because of the first priority here, this compound will be named not the triple bond, but the double bond. The triple bond here will not be taken first priority. The first priority will be taken by the double bond. Correct, guys? So, and here's some examples. As you can see, some examples here. 2 of them, that's ethane, single bond, correct? 1 double bond, ethene, eth, because eth is means what? Number of carbon, and then E-N-E, that's a double bond. If you had a triple bond, that's eth, the same thing, and then Y-N-E, that's for the triple bond. Here, E-N-E for the double bond. A-N-E for the single bond. So single bond, double bond, and here is triple bond, the ending. Correct, guys? And always the numbering, the double bond will take over the triple bond. Here single bond, 3 carbons, prop, see prop, and then you're ending ane. Here you have 3 of them, prop, the same thing, prop means 3, and then since we have double bonds here, ene, you add this ene here. Here, prop, and you have a triple bond, will be what? This is prop means 3, and the ine is the triple bond. Okay, guys.
So what would this be called? One at the top, 17?
Which one?
At the top in the red.
This one?
4 carbons.
This one here? Here? Which one?
I don't see where you're pointing. The 4 C's.
This one?
Yeah.
Okay, that will be 4, correct? That will be bute, correct? And then ene. And then you can see what's this group is. That's the triple bond will in whatever is the number is. You have to this is 1, so 1 butene, correct? That's the main one. But however, in number 3, you have a double bond, correct?
Would it be 1, 3 bute?
No, 1, 3 you have. If you said 1, 3, then you have you not designate. You have to designate the triple bond will be Y and E, correct? Number 3. So I will say 3 ine, that's designated double bond, dash 1 butene. You name it as a butene because that's your first text priority. And then you designate the triple bond always, this meaning the triple bond. Y and E means triple bond. So you have a triple bond there. So 3 ine, then dash 1 butane. So 1 means the double bond at number 1, and Y and E, that's not the priority, does not take a priority, will be 3. 3 ine, 1 butene. Make sense? Make sense? Okay, so taking this one out. Here just an example, you can look at them. So those are examples, and as you can see, those are straight longest chain. So those are straight longest chains. However, then we have here, we have a branched. So here we have branched groups or substituents, correct? So we have all this is straight, then you have, those are the branched one. The branched one in this case is a methyl, but they will not take the first priority. The first priority will go what? The double bond, followed by the triple bond. Then you look at the where is your substituents, where is your group? So here it is, that's number 1. Number of carbons 3. So this is 3, that's prop. Correct? 3 means prop. You go by the carbon number. That's prop. And then you have number 1. I'm just looking at the skeleton, the whole molecule. I'm not looking at the substituents. I'll come back to the substituent. One is here. The carbon is, the first carbon has a double bond, 1 propene. Correct? So now 1 propene, I have methyl is hooked up to what? To the second one, correct? Everybody is following? So I will say 2, the methyl is in the number 2. So 2 methyl, and then 1 propene. Meaning the double bond is hooked up at the carbon number 1. That's what it said. This is number of carbons, 3. Number of carbons, 3. And this is group here, the substituents or the branch group, is hooked up on number 2. That is the group here, the substituent, hooked up to carbon number 2. Make sense, guys? This is system, like a systematic steps, so you have to follow these systematic steps. But the main thing is the double bond will take over, single bond will take over the triple bond, correct? So, and you can then look at the others. Here this is the same thing, but here's number of the carbon will be what? How many carbons you have? Will be butane, correct? E and E. And where is attached? Number 1. 1 butane, correct? And the methyl group is number 2. So it will be 2 methyl, 1, number 1, butene. So the ene here is double bond. Number of electrons is 4. Where is double bond is hooked up to? This to the double bond, carbon number 1. Where is your substituent of the branch group? Hooked up to what number here? Number 2, correct? Yeah, number 2. And so on. It's a system. The main thing is, first, the skeleton. What is a skeleton? The longest straight chain. And the longest straight chain is made of 4 carbons, bute, here in this case, 4 carbons. And here is made of 3 carbons. Okay, guys? Make sense? Okay, so let's take this one out. Here's just an example. You can look into them again. We talked about them. And as I said, until now we are not taking any common or business names, commercial names. We will not rely on those 2, commercial or common names. We are looking at the always IUPAC name, the International Union for Pure and Applied Chemicals. We are naming those accordingly. So always the longest chain. That's your key here. First, you look at the longest chain. Where is the double bond? Double bond will take first priority over the triple bond. Where is it located? That's the longest chain. Long chain. We call this the backbone or skeleton of the molecule. Then after that, you locate where is your, you have a double bond, correct? So it has to be ENE ending. Ending ENE. Where is located this double bond? Look at the location. The lowest number is number 1. So it has number 1. This double bond is located. If there is an attached group or substituent, then you have to locate those two. So if you have more than one double bond, will be di-ene. If you have, for example, say 10 double bonds, what will be that? Dec-ene. So if I have 10 double bonds, 10 double bonds. So what will be my name? 10 means, I'll say dec, from deca, dec, and then ENE at the end. That's a double bond. How many of them? 10. Correct? Here we have 1, 2, 3, 4, bute-ene. So get the number of the carbons, and then you're ending with ENE. You have to look at how many double bonds you have. If you have a triple bond, you will end up with what? The same way. Just the ending will be different, like here, will be YNE. But again, you have to look at the number of carbons. This 1, 2, 3, 4, so it will be bute. That's number 4. So you have 4 carbons, and you have triple bond. Where is located? I have to look at the lowest numbering. Number 1. That's starting from here. Start always double and triple bond from the beginning of the bond, not the end, not 2. Not 2, that's not correct. That will be 1, correct? 1 butane, 1 butane. The YNE pronounced like yan, 1 butane. Okay, guys, so you can look at the other examples when we have this attached substituent or attached group to it. So this is other examples. The numbering, we talked about this numbering. Always look at the longest chain and look at the numbering of the double and triple bond. That's the lowest numbering, not the highest numbering, the lowest numbering of this double or triple bond. And if you have them both together, the double bond will take first priority, and the molecule will be named as a double bond, as E. And then the yan will be added with the numbering, where is this triple bond located, correct? So now we have the cyclic, the same way we did. There's nothing mysterious about it. Always your numbering the cyclic. So number of carbons first. So this is 5, like for example here this is 5. First, because it's cyclic, you can add always the word cyclo. This is a ring. This is a cyclo. Now, how many number of carbons? We name them that numbering that yields the lowest numbering of the here in this case double bond or triple bond. So I will say 1, 2, 3, 4, 5. Okay, guys? Can I number it like this? Here's the double bond. 1, 2, 3, 4, 5. Can I do that? Which one is correct? This or this? This is the correct one. Always, I start with the double bond with 1. The end of the double bond will be 2. I start with the triple bond with 1 or 5, for example. The end of it 6, carbon number 6, for example. So this is not correct. This is not correct. And you can see it if you attach any whatever attachment here. So if you attach chloro or any other substituents, that will be a big error there. That will be a big error. So, but this one here is cyclo, and then you look at the number of the carbons. How many carbons? Those are 5. So that would be cyclobent number. This is just the beginning of it. Then number of carbons, correct? Since here it's easy, I mean, we recognize there's only one double bond, we have no problem. So ENE. Here, you can, if you write here, cyclobentaene, and then if you write whatever is 1 here, it does not really matter. No need for this, because you have 1. Now, it will be different if it's what? Has 2 or 3. That will be what? That will be different. So I'll give you a 3-1. Here it is. Now I'll make here, this is 1, this is 2, those alternating, this is 3. So, can I put this 1 and 2 here? No. You start with the double bond, you end up with the double bond. So here it is. So this is 1. If I started here, that's my 2. Always start with the double bond, you'll end up, number 2 is your double bond. Not going out away from the double bond. I cannot put 2 here, that's not correct. Are you following me here? So 1, 2, 3, 4, 5, and this one will be number what? 6. The double bond has to have 2 numbers together. So 1 and 2, 3 and 4. They are adjacent to each other. 5 and 6. So what we call this one here? What we call this one here? That's a cyclo. Cyclo, okay. But it has another name. Cyclo, that's correct. You started with correct. Your approach up 100% correct. Cyclo, and is how many carbons we have? 6 carbons. Hex. Hex. And then what? Triene. Correct. However, triene means three double bond. However, this name has a specific name. This name, we use it as benzene, aromatic. This is aromatic. That's part of hydrocarbon, but it has a name called benzene. Those triple bonds are migrating. They are not located in one fixed place. They are moving around. So this one here called benzene. But the name of it is this. This is correct. Cyclotriene. Cyclo, hextriene. Cyclo, that's a cyclic ring. Hex means 6 carbons. Tri, number of the bonds. And how many of those number of bonds, double bonds? 3 of them. So we have 3 names. But the IBC said both names, but this is too long. We give it a name, call it benzene. But if you write this one is this is still correct. This is correct. But the IBC tell us that's too long. So we'll give it what? That's the basic core for the aromatic compound. Aromatic compound, from the word aroma, means smell or odor. Those organic compounds, they have very specific odor or smell. Now, the alkynes, alkenes, alkanes, single, double, triple bond, most of them with what? Odorless. Are you following me here? Only one here that start the odor coming in, and that's they call it the core of aromatic compound is benzene. Thus, it has very specific smell and odor. All the other ones, hydrocarbon, we have alkanes, alkenes, alkynes. They have mostly odorless. Yes.
So what I've been seeing is true. Is it possible to start counting at any of the double bonds? Because you started on top. Can I start at the bottom or on the side?
Oh, you can start anywhere.
Okay.
And that's the reason this here called, I can't really locate them 100%. So here it is. I start with this. However, this can go to the other side, correct? Here, here, and here. So, and therefore, this one is, they said, well, we don't know where the double bond is. We make what? Benzene always written as circle inside it. Circle means you cannot locate, you cannot number those double bonds, exactly. They are not fixed. Are you following me here? They are not fixed like a cyclic ring. Are you following? Everybody's following? So we write it like this with the loop inside. I mean, those double bonds are moving around. They don't stay in one place. So they are moving around, and therefore we write it. What's that?
Start counting anywhere?
No, really, you can't count those those triple bonds because they are moving around. They are delocalized. They are moving around. That's the structure of benzene. Here,
No, I mean for the double bond.
the double bond, you can
Start counting anywhere.
You can count anywhere. And that's the reason with the cyclohextriene is a correct name. We say benzene, since those triple bonds are moving around, it's very hard to number them. Where is your number one? Here? Or number one is here? Well, those triple bonds, you cannot fix them. You cannot touch them and tell them stay fixed in space. They are like in motion. They are moving around. So you cannot. So that's the reason we write the benzene is with the ring, cyclic ring, with the loop inside. Because we don't know where to number those double bonds because they are not localized in one spot in space. Make sense, guys? So, and you can look at the other naming, the same thing we named benzene. Benzene is cyclohextriene. Cyclohextriene. The name is correct. However, obviously this is too much, too long. We'll just get it the name benzene because that's the core of the aromatic compound. Aromatic compound different from alkanes, alkenes, alkynes of the smell. And that's the naming called aromatic. They have specific aroma or smell. The alkanes, alkenes, alkynes, they are odorless. Okay, guys? So, you can look at those questions here. We can, oops, sorry. Just pick up one and then you can do the other ones. If you have any question, you can still meet me in person or meet me in WebEx. So pick up any one of those and we can do together one of them. Pick up any one of those. I did not see them before, but pick up any number we can do.
Can we do
Number 4? Let me see. 1, 2, 3, 4. Okay. So, how many numbers of the longest chain or the whole body? How many we have? How many we have? 4. So, and this is what? Cyclo. So this will be looking like this. Those are 4, correct? Cyclo, butene. So you can pronounce cyclo, that's a cyclic, but 4, and then ene, you have a double bond here. Correct? You have a double bond here. So the double bond is not really numbered. Is it numbered? I can't see it. No, it's not numbered. So let's put, if it's not numbered, we can put this one here. Correct? So, because this is on here, can I put 1 and 2 here? 3 and 4? Is this correct numbering? I want to hear it. Come on, guys. Don't sleep on me. Can we do this? No. Always you start with the number of the double bond and the triple bond, you will end up with it. So this is not correct. The correct one will be, so the correct one, you start with 1, you end up with the second for the double bond, or the triple bond, the same way, 3 and 4. So now, It's not designate where the double bond is. It does not tell us where the ene is. We don't know. So then we have, since it's not, we give it to 1 for the first priority. The attached group is 1, 2 methyl. So 1 and 2 here are what? Methyl. Since they are the same way at the same orientation, this will be called cis. Cis 1,2 dimethyl cyclobute 4-ene. We have to add the word cis. So this missing here. Cis. Why cis? Because they are the same way, the same orientation in space. If one is here, the other one the other side, there will be trans. Yes.
Question. So, I learned that if it was on the side, it wouldn't be minor.
Was that?
If it's on the side, it wouldn't be minor. It wouldn't be cis or trans.
Yeah, this is cis because they are the same. They are the same in the same orientation. But if one is the other side in space, correct? So this one here is carbon. So carbon. So all the carbon is 4. So you cannot have a trans because you don't have a hydrogen available. Otherwise, the carbon will have five valence electrons, and that's violation. The only thing you have in this case, in this structure, only cis. You cannot have trans.
Yes, I understand that. But,
Yeah.
Usually the cis of the trans is either at the bottom or the top. So the side, I had a question, and the side was minor.
So let's look at this. Here you can see them. So here it is. Versus C double bond H CH3 CH3. If you have this is on plane, so it's sticking down the plane, the 2 metals here, they will be cis. The upper hydrogen still cis. But if this is the plane here, and one is sticking in the top, one is sticking in the bottom of the plane, that will be trans. Make sense?
She's looking at it as like the movie on the top and the bottom on the same side, not like this. She's saying it like this.
Well, whatever, yeah, that's, you can visualize this way, yeah, whatever. It's the same thing. It's the same thing. We don't disagree. We agree. I mean, you can look at it. But this is the double bond and the triple bond always flat in a plane. And those substituents are sticking out. One in the top behind you, and one in the top in front of you, one at the bottom behind you. Make sense? Yeah. So, but as I said, you have a 3D molecule and you want to represent it in 2D piece of paper. It's very tough. Are you following me here? It's very, very tough. It's almost impossible to draw a 3D molecule in a piece of paper which is 2D dimension. So in order to have it really, you have to have special software, 3D on 3D. Then you can visualize it much better. But here I have the screen here, computer screen is a 2D. The molecule is 3D. So it's very hard. But you can visualize whatever you like, whether they are sticking this way, or they're sticking the other way. The main thing is they are sharing the same space. If they are sharing opposite space, that's a trans. Okay, guys? So, let's take this one out. You can look into the other ones. Please look at them, and if you have any question, just talk to me. Then in person, I meet with some students online through the WebEx. So just we have to, through the weekend, you have to let me know, because I have sometimes meetings with other professors on the weekends. Like this Saturday we have meeting, so I might be not able, but you have to let me know what time you are coming. And this is some common names. again, common name, commercial names, we have nothing to do with it. You don't have to memorize it, but it will be nice. It will be a plus to know those commercial names or common names. So the two carbons with double bonds called two carbons is eth, correct? Eth, and then the double bond ene. So eth, two carbons. The one carbon meth, two carbons eth, three carbon prop. So then ene's a double bond. This has a common name called ethylene. Ethylene, somebody will tell me where you use ethylene? Polyethylene, the plastic one, the plastic bags, guys. See polyethylene? The ethylene can be polymerized, and then as you will see later on, and you can make polymers out of it, plastic bags. See-through plastic bags. Somebody has seen, you have seen the see-through plastic bags. You can put your fruits, your potatoes, whatever your food inside it. Those are polyethylene. That's ethylene here. The commercial name of it, the common name. We are, you are not allowed, I mean, you are allowed to look into them, but it's up to you. If you want to memorize those, that's fine. Ethine, the two carbons and one single triple bond, one triple bond. This is triple bond here, and eth is two. Called, it has a name, acetylene. Where we find this one here? Come on, guys, somebody will tell me. Acetylene. So I told you ethylene is the bag, plastic bags. And acetylene where? You know that. Come on, guys. Don't Google it. You can't tell me. Where? Don't Google it. If your muffler of your car is broken, you go to the guy to fix your muffler. So the welding of a new muffler has to use acetylene. So acetylene is hydrocarbon that's used in welding with oxygen. So the flame is so high that can ease the melt of the metal, correct? So acetylene is used in welding, especially in the exhaust, in the exhaust cars. You will see a big tank. The guy has a big tank, is using it, use the flame of it with oxygen. Propylene or ENE, that's double bond. Prop is three carbons. Where we use this propylene? Come on, guys. Polypropylene is used to make those piping, those plastic pipes underneath the sink. See those white pipes, not metals, not stainless steel metal. No, those are piping. Polypropylene is used for those type of piping make. The other one, the polyethylene with two carbons, is used for the plastic bags. This one is used for the piping, plastic pipes. The plastic pipes mostly under the sink. You'll see them under the sink. So again, you don't have to memorize those things. It's just that's an extra, that's a plus information for you. You will not be asked, not in the final exam, or nobody will ask you about these common names. But it's nice to know in your house what this is made from. And this is further phenyl chloride. That's a phenyl. This is a group called phenyl. Again, that's a common name. Oops, sorry. Phenyl group. This is allyl group. So, and then you can use an example of this. Phenyl chloride is used again in piping, much more stronger pipes this time, and the allyl, those most of the time are used for this one, maybe in painting, this one. So, but anyway, so that's the examples. You should not be worried about. At least you know there's a lot of common names and commercial names we are not really interested to know about. about details about this thing. Now, double bonds and triple bonds, it looks like, again, the double bond, it has an hybrid double bonds. It's a hybrid, it's making of hybridization of S, one electron of S, one S, B, and two in electron, sp2, so sp2 hybrid. So if I have carbon here, this will come sp2, this one sp2, the bonding, the hybridization between the two carbons to form this double bond called sp2. This is sigma, sigma sp2. So this is one of them. The second one here is bi or bi bonding. So that's the bonding of the whole thing. Again, this one here has to be taken in 1150 in higher chemistry, not 1151, in principles of chemistry. So you know this hybridization, those carbon, they form bonding by hybridization. Hybridization means mixing. They make a hybrid. Hybrid means mixing of more than one thing. I have a hybrid. I don't have a hybrid car, but if I say I have a hybrid car, meaning I have what? Two systems in it. Somebody will tell me which of those two systems can be gasoline or electrical, correct? Hybrid means a combination of more than one system. Can be hybrid of 2, 3, 4, whatever that might be, correct? But more than one. So that's a hybrid. So, and those, when they come together to make the double bond or the triple bond, they have to come together with the specific hybridization to utilize this bonding. The triple bond is the same thing. They have their sigma is sp hybridization, correct? So this is sp hybridization, and this is, and the single bond here is single bond. This is single here. Single is sp3. Single bond sp3. So let me make a table out of this so you can follow. Just hold on, I'll make a table for you guys. So here it is. Bond type, hybridization. Now, what's the angle of this hybridization? Correct. And what is the geometry? Means the shape. The shape. So if I have a single bond, which is CC, then the hybridization is sp3. The angle is 109.5 degrees. And the geometry is tetrahedral. Okay, guys? That's not really well done in the PowerPoint, but at least we know. I have a double bond. See double bonds here. Okay, guys? And this is sp2, and the angle is 120 degrees. This is 195, and this is trigonal planar. Trigonal planar. And if I have a triple bond, this is S triple bond, C triple bond, and the hybrid is SP. The angle is 180 degrees, and it is linear. So with this information, I would like you to memorize it because it might be in the final exam coming, ask you about what type of hybridization, if any, with the triple bond. Triple bond has sp hybridization, and the means one electrons. When I say s, for example, p3 means how many orbitals I have. S has 1 and 3, so I have 4 orbitals here in this. Okay, to make those bonds. For example, sp2, I have how many? 1 plus 2 make 3 orbitals. Those are single bond, and so on. So at least you have this information for yourself. So look into this information, is very important. So anything here? Everybody has it? Everybody has this? Everybody has it? Can I take it out? Okay, let's take it out. Let's go back to yeah, that's all about here. Whatever you have here, that's we covered this, we covered the other one, so you don't have to memorize this memorization, but all this stuff is here. Now here is what we said. We talked about this trans versus cis. So you can see sometimes you have restriction in space. You can have only trans, you cannot have cis. In this case here, we don't have cis, we can't have cis. So there is space, we call this type of this, we call it space restriction. So you can have restriction. So you can't have cis in this. So this type of molecules is only does have cis. That's our orientation in space. Now, I cannot really tell you how to visualize those double bonds in space. It would be nice if we have a model or computer software show us why we cannot get cis out of this. Okay, guys, but at least that's beta carotene. So it said carotene, E at the end. So that's the double bond, and plenty of double bonds you have. That's and this group here is an aldehyde group. Aldehyde groups are very distinct in their aroma. They have specific smell. So, this is cis and trans. You can see the cis and trans. They are different in physical and as such in a chemical properties. So not only the orientation is affecting their physical and chemical properties, and you can see they behave differently chemically and physically. So the boiling point is 60 for the cis. The boiling, this is trans is very low, 47 degrees the boiling point. And what you have, melting point, minus 80. Melting points minus 50. So you can see the orientation in space is very, very important, because that will lead to isomers that's really different. Although they have the same molecular mass, the same molecular mass, and the same number of the same type of atoms. However, the orientation in space is differently, will lead to what? Lead different physical and chemical properties. So you can't expect those two here will react identically 100%. They have different physical properties, and as such, they will have different chemical properties. Correct? So now you can see this is non-polar. That's one of the physical. This is polar. Somebody will tell me why. Well, it turns out to be those dipoles, the chlorine is higher in electronegativity than carbon, so the dipoles will be ruled this way, and from here the dipoles will be this. Those two dipoles are the same strength, opposite direction, so the net dipole will be 0. Net dipoles is 0. Correct? Why? Because they are they have the same strength but opposite direction. Here, this dipole here, carbon is always most electronegative. So here they will add itself up. So you can look at the difference between electronegativity between this and this, then you add them up. That will be your dipole here. So the dipole here, in this case, dipole is not, or dipoles are not zero. So if you look at the electronegativity difference, both sides, they are the same strength but the same directions. Both of them the same directions. So this is polar, this is not polar, for the fact direction of the dipoles. Okay, guys, so take this one out. Chemistry of vision, don't worry about this. I'm not going through this. That's a biochemistry and a medical school chemistry. But those are here just the idea of, again, you have cis and trans, physical, correct? Physical properties and chemical properties are different. Some of them might be polar, some of them will be not polar, as we've seen before. So that's you can see here 1 butene and 2 butene. The question is, which one will have, out of those, 1 butene or 2 butene will have cis and trans? It turns out to be the 1 butene, if you flip it the other way, will be the same thing. So this is identical to this. They are the same molecule, correct? Yeah, because look at this. That's the same direction, both of them. That's the same molecule. Just you flip it up and down. But here is totally different, because then the methyl group is sticking out or sticking down, dangling down, and here one is the opposite to each other. So this is possible with this, but this molecule is not possible. So 1 butene does not make cis and trans. The 2 butene does, and that's what it says here. Again, as I said, cis and trans, they differ in their physical as well as chemical properties. So that's the this is where the cis and trans, when the flipping of the double bonds here, you can rearrange the double bonds and you can get the trans. However, you cannot get you can get out of this if you put an enzyme. Then you can break the double bond and rotate it. So you can. So here it is. Normally you have in nature cis. Can you make out of it trans? You have a trans, but can you make out of this cis? So this is cis, this is trans. The answer is you can, but you have a catalyst there. You have to have a catalyst. The catalyst is enzyme, special enzyme in the liver. You can transfer them back and forth from cis to trans, trans to cis. So, but don't worry about this. At least you know, as I said, those we need the special software to visualize this. So you have to break first this bond. This double bond has to be broken, and then rotate the whole molecule to get the cis. And that is shown here. Let me show you here, guys. This is shown here. In this one here. Here it is. Show you how you can make out. Those are cis guys. This is cis. This is cis. Same orientation space. Now, how in the world I can make out of them trans? This is cis. This is now is trans. Well, that's only possible if you rotate the double bond. And we talked about double bond and triple bond. They have restriction. You cannot rotate them. Single bonds easy to rotate. Easy, very easy to rotate, correct? But the double bond and triple bond cannot. So you have to have a catalyst, an enzyme. You have to have a catalyst, palladium. Any catalyst can do break the double bond and you get single bond. Then it can be rotating in space. This is when it starts, the double bond is out, you have single bond, then it starts what? Rotating itself. So here this is still free radical, still carbons, there's still valence electrons still on each carbon. Then you rotate, see the rotation here, this rotate this way and this go this way, and then you can finish your thing and then you get a trans. Again, those processes are not possible in normal conditions. You have to have a catalyst to help you to break this bond, because rotation is restricted in the double and triple bond. It's not allowed unless you use a catalyst or an enzyme on them, so it breaks the whole thing, making a free radicals, and free radicals can rotate in space and they get out of it a trans, correct? But in normal condition, that's impossible. Normal condition, that's impossible. You have to have a special catalyst for this or enzyme to do this. So now, what is the chemical properties of the alkynes and alkenes? It turns out whenever I have this, we called here, this double bond and triple bond, they will call them hungry. Hungry means what? They need some food to be fed. Meaning I can add to them, give them some food. Correct? Single bond is already, all the carbons has 4 bonds, correct? Everything is full. You cannot feed into this. You can add nothing. But here, if I open this, one of the single bond or a triple bond, if I have a triple bond and open it, here it is. So then you'll have 2 bonds, 2 things you can add to it, correct? So here it is, the double bond will be opened up, and then you can add to this, because carbon, how many carbons we have? How many hydrogens? 4 hydrogens. So 1, 2, 3, 4. You open up one single bond, then you can add this molecule there. So the double bond and triple bond, you can add to them any other chemicals, any other compounds, double bond, triple bond. Single bonds you cannot. You can only do this through free radical chemistry. You break the molecule of alkanes into free radical, and then from there you can add to them. Okay, that's totally different and very, very tedious type of chemical reaction. But this double bond and triple bond, you can open them very easily, and then you can add to them. Here is an example here. You have example here, double bond, you have chlorine, double bonds open, you can add, see here, double bond here, take one single bond now out of this, and then you can add chlorine here, as this one here. Everybody's following? So the addition reaction is one of the chemical properties of a double and triple bond. That's easy. That the alkanes, the single bond, you cannot add. No addition reaction is allowed, correct? Unless you go different path, which is free radical chemistry with that. So, we have still 5 minutes. We can finish some stuff here. And this is just an example. Again, I can open up the double bond here, when single bond here. I can open those here, and I can add, correct, here. So the addition, this one here is this one here. Okay, those here. Then add more, then you can add to this other single bond here. Open here, you get here and here. Correct? So the double bond will open up and you can add to it. Okay. So hydration, hydration means you add hydrogen, and you can open up a double bond here with the single bond, and then you can add hydrogen to it. If you add OH, then the OH will be in one of them, and we know where will be the OH. We'll know where the OH will be. So this is, you can add hydrogen by itself, or you can add H2O to this and making alcohol. Now, this is an example. This is another example here. You open up a double bond, again, the same way we did. Open the double bond, and you add your OH, H. So one carbon will have the OH, the other carbon will have the H. Correct? So, now, as you can see, you have OH. OH is making the molecule is polar, so this makes them polar here. Here you don't have any OH. That's a polar group. Here you don't have any polar group. So this molecule is non-polar. This molecule is polar here, and this polar group makes the hydrogen bonding. You might have heard this one in 1151, hydrogen bonding. So now how we can distinguish between double and triple bond in the lab. So in the lab, it's easy. We make just the bromine test. So the bromine test, meaning here's alkanes. Here, if there is no reaction, here is no reaction. Here is reaction. The bromine is still there. Bromine is present still. Correct? I added to two test tube. Here, bromine is gone. Bromine is disappearing. Disappearing. So, what's happened? Which is which? It turns out the alkanes, they don't add. No addition, correct? So here, no reaction means no addition. So this following? Of bromine, in this case. So this one here has to be what? Alkanes. Single bond. Single bond, you don't add to them. The double bond, you will add to them. So this one can be alkenes or alkynes. Triple or single bond. Why? Addition is allowed here. Addition is allowed. And therefore, the way we can distinguish in the lab between alkanes, alkynes, and alkenes by the bromine test. If the bromine stays, means we have single bond. No addition is allowed. Bromine does not react, does not add itself to the molecule. If the bromine add itself to the molecule, it will be what? It loses its color. That's the color of bromine. This is color, bromine color. So it's no reaction. So the double bond and triple bond, the bromine does add itself to the double and the triple bond. So that's the best type of chemical or experimental setup to distinguish between alkanes and alkynes and alkenes. Alkanes will not add up bromine. The bromine will stay as is in its color. But the alkenes and alkynes, they will add this bromine, and the color of the bromine will disappear. I'll stop here, guys, the recording. We'll meet next week to finish the chapter. We are at the end of the chapter.